All right, hey guys, today we are going to look at the dot product of two vectors. Right, the dot product is especially useful in applications of physics or engineering. All right, and so our definition for the dot product is what you see up here. So let's go ahead and write this down. If we have vector u, which has a horizontal component of a1 and a vertical component of b1, and vector v, which is going to be our a2, b2, the dot product of these two vectors can be represented right here. So we say the dot product of u and v is equal to, and what we do is we take the horizontal components from both vectors and we multiply them together. Right? We also take the vertical components of both vectors and we multiply them together. So we have a1 times a2 and b1 times b2. Then we add those two products. So you'll notice because we're adding them, we don't end up with two numbers anymore. We just have a single number. Right? The dot product, when we take the dot product of two vectors, we do not end up with another vector. Right? What we end up with is a real number or a scalar. If we look at this first example, we're going to do the dot product for vectors u and v, right? So if I want to take the dot product of u and v, right, remember I'm going to take my horizontal components and multiply them together. So that's going to be 3 times 4. And I'm going to add that to, and I'm going to do the same thing with my vertical components. So I'm going to take -2 and multiply it by 5. Right, so when I do that, I have 3 times 4, which is going to give me that 12. And then 2 times 5, I should say -2 times 5 is going to give me a -10. So I end up with the answer of 2. The dot product of u and v for this first example is equal to 2. All right, and here's the typed version, right? All right, now we can do the same thing for this next example. We're going to find the dot product of u and v. The only difference is it's in terms of I and j instead of the angles being written as angled brackets. Right? But the process is still going to be the same. If I want the dot product of u times our u and v, I'm going to take my horizontal components, so I'm going to take 2 times 5, right? And I'm going to add that to the product of my vertical components, so 1 times -6. Right? When I multiply, I end up with 10 minus 6. All right, so the dot product of u and v for the second example is going to be 4. There we go. All right, so the dot product is something that we use, right? And we have to check our properties just like we did when we were adding vectors and all of that, right? And the nice thing is our properties still apply when we're dealing with the dot product and vectors, all right? So the dot product of u and v is equal to the dot product of v and u, all right? And we can go ahead, and you don't have to write this down. It's like the last one that I showed you guys. It's just to make sure that some of those properties that we're so familiar with when it comes to scalars, right, still apply and still work with vectors. Oops, I went too far. All right, so what we're going to look at next, the dot product helps us find. So we're going to look at the angle between two vectors. So we're going to say the angle theta between, in this example, vectors u and v. Right? Theta is always going to be the smaller of the two angles formed by the representation of u and v. Right? So we have two angles right here. If we look at u and v, we have this first angle, right, on the inside, but we also have this angle on the outside. Right? When we're talking about the angle between two vectors, that theta, we're always going to be talking about that smaller angle. Right? So theta should always be between 0 and pi. It shouldn't be larger than pi, right? Because if it's larger than pi, then that means it's gone more than halfway around, so there should be a smaller angle. Okay, what we use is the dot product for Okay, is we have this thing called the dot product theorem, right? And it says if theta is the angle between two non-zero vectors, u and v, then we have our dot product theorem, which is right here. The dot product of u and v is equal to the magnitude of u times the magnitude of v times cosine theta. Right? This is useful because it allows us to find the angle between two vectors if we know the components of the vectors. Right? So this second equation, guys, is actually the exact same equation as the dot product theorem. The only difference is we solved for cosine theta. All right, so we solved for cosine theta, and when we do that, we get the dot product of u and v divided by the magnitude of u times the magnitude of v. All right, remember, we know how to find the magnitude of a vector. If we want to find the magnitude of a vector, we take the square root of a squared plus b squared. We take the horizontal component, square it. We take the vertical component, square it, add it together, and square root. Right, and that gives us our magnitude. So what we're going to do next is we want to find the angle between the vectors u and v. Right, so to do this, I'm going to use the formula that we just wrote down. Cosine theta equals the dot product of u and v divided by the magnitude of u times the magnitude of v. Right, if we want to start solving this, I'm going to look at the numerator. I'm going to do my dot product. I'm going to do my magnitude for both of them. Kind of split it up for me. So I can start off in the numerator. My dot product of u and v, I'm going to take 2 times 4, right? And I'm going to add it to the product of my vertical components. So I have to take 5 times negative 3. So plus 5 times negative 3. Right, now to find the magnitude of u, that's going to be the square root of 2 squared plus 5 squared. All right, and we know that 2 squared gives us 4 and 5 squared gives us 25. Right, then we've got to do the same thing, but we've got to find the magnitude of v. So I'm going to take the square root of 4 squared plus negative 3 squared, and so that gives me the square root of 16 plus 9. All right, well, we know 16 plus 9 is 25, and the square root of 25 is just 5, so I can simplify this a little bit. All right, I can say that this is equal to negative 7 over 5 times the square root of 29. All right, now at this point, we're trying to find theta, so we've still got to get this theta alone. And so to do that, we're going to go ahead and inverse cosine both sides. All right, when I do that, I'll end up with theta equals the inverse cosine of negative 7 over 5 square roots of 29. All right, we could use our calculator. Okay, this is definitely not one of our significant values on the unit circle, so we would need to use our calculator for it. All right, we're just going to type in that inverse cosine, type in the 7 over 5 square roots of 29, and we end up with an angle of 105.1 degrees. All right, so the angle between vectors u and v is equal to 105.1 degrees. All right, so the last thing we're going to look at is talking about the angle between two vectors. Right, we have a quick and easy way to identify if we have two vectors that are perpendicular, okay, if they make a 90-degree angle. So two non-zero vectors u and v are perpendicular if and only if the dot product of u and v is equal to 0. So if we test this out, we have two examples up here. We want to decide if these vectors are orthogonal, if they are perpendicular to each other. Right? We can do that by just taking the dot product of both of them real quick. So if in this first example, I take my dot product of u and v, I'm going to take my horizontal components and multiply them. So I'm going to take 3 times 2, and I'm going to add that to the product of my vertical components. So 5 times negative 8. All right, well, we know 3 times 2 is 6, plus 5 times negative 8 going to give me negative 40. And so 6 minus 40 is going to give me negative 34. Right? This does not equal 0, so this one is not perpendicular. Okay, that's all we have to do. Just check it out. Do that dot product. If it equals 0, it is perpendicular. If it's not equal to 0, it's not perpendicular. So if we look at the next one for B, right, we'll do the same thing if we want to decide if these two vectors are perpendicular or not. We're going to do the dot product of U and V again. Take my horizontal components, 2 times negative 1. All right, and then find the product of my vertical components, 1 times 2. I end up with negative 2 plus 2, which does equal 0. All right, and so because when I took the dot product, it equals 0, all right, these two vectors, U and V, are perpendicular. Okay? All right, so that's our notes for now. So let's go ahead and start practicing with some homework over this whole dot product and angles between two vectors.